Yes.
Okay, great. So as Valerie said, I will talk about the targeted analysis of sterols and related compounds. So start with an overview. So we're going to be looking at the lipid category of sterol lipids and the main class sterols, and we'll be focusing on the cholesterol and the derivatives, the subclass of cholesterol and derivatives. So an outline of my talk, we'll start with a little bit of introduction. Then I'll talk about a problem in sterol analysis, which is autooxidation. And then we'll move on to some methods of sterol analysis, which I've called classical, modern, and newer developments. So in this talk, I'm really going to concentrate on the analysis of cholesterol precursors. So as I've got, as you can see here, I've got the pathways of cholesterol biosynthesis, two pathways, the Block and the Candice-Russell. So we'll be considering the analysis of the cholesterol precursors, but mostly I will focus on my own real interest, which is on the analysis of cholesterol metabolites, and we'll focus on one particular family of metabolites, the oxysterols. So I introduced these molecules to you, I think it was on Monday, but a couple of slides of revision will follow. In this talk, I will not talk about the analysis of sterol esters, as that was covered by Bob Murphy on Tuesday. Okay, a few words about oxysterols. So they're formed in the first steps of all cholesterol metabolism, and they are oxidized forms of cholesterol. Basically, they're cholesterol molecules with an added oxygen functionality. That might be a hydroxyl, a ketone, or it could be a carboxylic acid. They're intermediates in bile acid and steroid hormone biosynthesis pathway. They act as transport forms of cholesterol in that they will cross cell membranes much quicker than cholesterol will, so they can act as a method of returning cholesterol to the liver, really. But the most important thing about the oxysterols is they're biologically active, and that's why we're interested in them, and that's why many other people are interested in them. So just a few words about the biological activity of these molecules. I did mention this a little bit on Monday. So they inhibit the processing of SREBP2 to its active form. So essentially, they repress cholesterol biosynthesis. They're ligands to the LXR, liver X receptor, so they promote cholesterol efflux. So overall, they will reduce the cellular content of cholesterol. They're also ligands to G protein coupled receptors. So for example, this one, GPR183, which is also called EBI2, and this is a pro-inflammatory GPCR. They're also ligands to the GPCR, which is called smoothened, and this is important in the hedgehog signaling pathway, which is important for proper cell differentiation in the embryo. So there are numerous activities of these oxysterol molecules that make them interesting molecules to analyze. However, when we analyze oxysterols, and this is also true for all sterols other than cholesterol, oxysterols, they're present in essentially all samples against a very great background of cholesterol. There's usually more than 1,000 times more cholesterol than any particular oxysterol. So that's an analytical problem in itself. What's more, the biggest problem really is that cholesterol is prone to autooxidation and generates oxysterol artifacts. So if you have a sample containing high levels of cholesterol and you're not careful with it, then you'll get autooxidation of that cholesterol and you'll get artifactual oxysterols formed. Some other issues with oxysterols, they're thermally labile, so you can't heat them up too much, and they're poorly soluble in aqueous solvents, which can make LC more challenging. Another issue with oxysterols and sterols in general is that they have a weak chromophore and they're comparatively difficult to ionize. So compared with the phospholipids, they're very difficult to ionize. So these challenges that we have here, they're particularly important for the oxysterols, but they're also equally relevant for the cholesterol precursors. So the biggest problem we have when we're analyzing oxysterols is the worry of autooxidation. So this is the oxidation of cholesterol by oxygen in the air. So essentially, whenever you handle your samples, it's almost impossible to work in an air-free atmosphere. And cholesterol is particularly susceptible to oxidation at the 7 position. So just next to the carbon double bond. And an oxidation will give us 7 beta hydroxycholesterol. It will give us 7 alpha hydroxycholesterol and also 7 oxocholesterol, also called 7 ketocholesterol. So these can all be formed by just leaving your sample on the bench. We can also see oxidation of the double bond, giving us 5,6 epoxycholesterol. And that can be hydrolyzed in acid solution to give cholestein 3 beta 5 alpha 6 beta triol. So these two can also be formed as sample workup artifacts. So the real big problem we have here is that these molecules are formed ex vivo during storage and sample workup, but they're also present endogenously. So we actually have autooxidation or free radical oxidation of cholesterol in cells. So all of these autooxidation products can be formed both artifactually, and they also can be formed endogenously. They can be formed endogenously by, as I said, free radical reactions. They can also be formed enzymatically. So when you do an analysis and you analyze, for example, 7 beta hydroxycholesterol, you're always worried, is that 7 beta hydroxycholesterol real? Is it really from my sample, or is it from sample workup? And this is the real problem we have in oxysterol analysis, and we must be aware of it at all times. Okay, let's now look at some analytical methods. So these analytical methods, they were actually designed for oxysterol analysis, but they're all equally applicable for analysis of cholesterol and cholesterol precursors. So I've classified the methods as classical, modern, and newer. So the classical method for oxysterol analysis is GCMS. Then we have modern LCMS methods. And then what I've called the newer methods are LCM and LCMS methods with derivatization. And we'll look at different methods which I've sort of highlighted from my own reading and experiences as perhaps the methods to try first. So the classical method for oxysterol analysis, as I've said, this is GCMS. And this is probably the gold standard. And the gold standard of all the GCMS methods is described in this paper from 1994, which comes from Ulf Dix-Velusi and Ingmar Björken in Karolinska Institute in Stockholm. And almost all the GCMS methods used today for oxysterol analysis are based on this method. So if you want to do oxysterol analysis by GCMS, I would recommend read this paper by Zlatovic. Okay, let's have a look at this method in a little bit more detail. So the method works well for tissues and also body fluids. Let's work through the method, and let's take plasma as our example fluid. So in the first step, plasma is collected in EDTA containing tubes. So the EDTA will chelate metals. So that it will chelate any iron present, and that will prevent the Fenton reaction occurring, which results in autooxidation. In their containers, they also have BHT, which will also stop autooxidation, and they immediately add internal standards. So they add deuterated isotope label standards. Now, most of the oxysterols and sterols, which are present in plasma or in CSF, they're present in the esterified form. They're present esterified with fatty acids. So in a first step in this method, the esters are hydrolyzed by base. So they use 0.35 molar potassium hydroxide in ethanol. So this hydrolyzes the esters to give us the free oxysterols and free sterols. They then, after 2 hours, they then neutralize with phosphoric acid, then do an extraction into chloroform. They then do normal phase extraction. So, yes, not normal phase, solid phase extraction. So this is very important, and it allows them to separate the oxysterols from the cholesterol, which is going to be in 1,000-fold excess. So as they're doing normal phase SPE, then the cholesterol and the cholesterol precursors, they will come off the column first, and then the oxysterols, because they're more polar, they will come off later. So they've got a fraction now which is free from cholesterol, so they remove the problem of further autooxidation. They then do derivatization. They derivatize the hydroxyl group to trimethylsilane ethers, and then they run GCMS. So this is a incredibly well validated method. It was, as I said, it was first reported in or described in the 90s, and it's still being used in the 2020s. So it's a really well proven method. So if you like GCMS, this is the method I would recommend. Okay, let's now move on to what we might call modern methods. So I guess ever since electrospray was developed, there's been a movement to replace GCMS with LCMS. So it's not surprising that along have come nice methods for the LCMS analysis of sterols and oxysterols. So now we will talk about some LCMS methods. And of the different LCMS methods out there, one of my favorite methods is the method that is described in this paper in JLR, developed by Jeff McDonald in David Russell's group. So these Jeff and David were were part of that first lipid maps group, where we saw a picture of the guys shown by Cameron yesterday. So this is a nice LCMS method developed by Jeff, and he's used this method extensively. And I think the most impressive study that I've seen on oxysterols is actually this study here by Jeff and David Russell and Ashley Stiles, where they actually analyzed over 3,000 plasma samples looking at 60 different sterols. So this is quite a lot of work, and it's a very impressive paper. So let's have a look at Jeff's method. So again, we're starting with plasma, and we're collecting the plasma in EDTA containing vacuum containers, and we add BHT, isotope label standards. They then do a extraction into chloroform and methanol, and again a hydrolysis with potassium hydroxide, 35 degrees, 1.5 hours. So they're hydrolyzing the cholesterol ester, the oxysterol esters, so you get the free oxysterols. They then added PBS and did a liquid extraction to get the oxysterol fraction. They then did, just like the previous method, they then did a normal phase SPE. And in the normal phase SPE, again, cholesterol and cholesterol precursors will come off first, and the oxysterols will come off later. And then they will run the oxysterols by LC-MSMS. So in the LC-MSMS method, they're using ammonium acetate as an additive. So for oxysterol analysis, they used electrospray, while for sterol analysis, they used APCI. So I'll just show you here a couple of MSMS spectra of oxysterols. And really the point I'd like to make is that in this particular case where you've added ammonium, you get the ammonium adduct as the parent ion. But when you fragment these molecules, when you fragment the ammoniated molecular ion by MSMS, you get rather uninformative fragmentation patterns. You see the loss of water, and you see the loss of two waters, the loss of one or two waters. So this is good if you're going to do MRM, because you get a nice intense fragment ion, but it's not so good if you're interested in structural information, because the fragments are really down in the grass here, other than the loss of water. If we're looking at the sterols, as I said, they're using APCI. Then they tend to get the M plus H minus water. But in the MSMS, they do actually get quite a lot of fragmentation, but the fragmentation patterns are rather confusing and not hugely informative. So a sort of a summary of Jeff's method. So it's working on MRM, it's LCMS method, work on MRM detection. Sensitivity is good, 50 picograms on column. Limits of detections are good, nanograms per mil. They're assaying 60 sterols, so that's a very, very impressive number. In plasma, they routinely find something like 22 oxysterols and sterols. The throughput, they can work up about 50 samples in a day. This is done manually. With a robot, obviously it'll be faster. Some of the drawbacks of the method, as you know, all methods have got advantages, all methods have got disadvantages. Well, perhaps some of the drawbacks of the method: the MSMS spectra provide little structural information, and IDs are really based on chromatographic separation and the availability of authentic standards. You really need to be able to separate out all the oxysterol isomers, and you really do need authentic standards for all the analytes. So again, this is a very good method. I would say it's complementary to GCMS. It's no better, it's no worse. Really, beauty is in the eye of the beholder here. So if you like LC, this is good. If you prefer GCMS, then the Dick-Velucci method is good. Okay, let's now move on to what I might call newer methods for oxysterol analysis. And in these methods, we incorporate a derivatization step. So the idea of incorporating a derivatization step is to actually improve the mass spec response. Because oxysterols and sterols in general are neutral molecules, they don't ionize terribly well by electrospray or by APCI. So over the years, people have tried different methods of derivatization to actually improve the ionization, to improve the signal. And we'll just go through 3 different methods of derivatization. So the first method we'll go through is the derivatization to picolinic acid esters. So this comes from the work of Akira Honda, and he published this nice paper in 2009 describing the method. So as I said, we're making picolinic acid esters. So here's a picolinic acid ester. So we started off with an oxysterol, actually 24-hydroxycholesterol, and it can be derivatized to the diester. So let's have a quick look at the derivatization reaction. It's quite simple. So we have picolinic acid ester, and we have a catalytic mixture, really, which is pyridine, dimethyl alanine, and this, let's see, it's a nitromethyl benzyl acid anhydride. So this, and you also got triethylamine. So this is basically a catalytic mix. So the picolinic acid will form an ester with the alcohol groups of the oxysterol. So you generate the double derivative, and what you find is that the picolinic acid ester tends to chelate sodium ions. So the picolinic acid ester gives you strong sodium adducts. So this improves the ionization of the molecule because we're easily able to pick up these sodium adducts. And what's nice is that the molecule will also fragment via MSMS to give you useful fragment ions. We see a fragment ion at 146, which corresponds to picolinic acid plus sodium, or alternatively, we might see a fragment ion, which is the M plus sodium minus 123, which is the M plus sodium minus picolinic acid. So you get fragment ions, which again going to be useful for MRMs. So if we quickly go through the Honda method, again, we're taking serum as our example starting material. So serum, again, we've got BHT and added that internal standard at the beginning. So as we discussed yesterday, it's really important when you're adding your internal standard to add it as soon as possible. So you're going to minimize your sample. Well, basically, you'll maximize your correction for sample loss. So you've added your internal standard. Again, they're doing a hydrolysis in potassium hydroxide to hydrolyze the esters into the free oxysterols, then do a hexane extraction. An issue with this derivatization reaction is that it's important that the reaction must be done in a dry environment. So after your hexane extraction, it's necessary to dry the sample down before you add the catalytic mixture. Derivatization occurs at 80 degrees for 1 hour. They then do another hexane extraction. So this works quite nicely, and they extract the derivatized oxysterols, but leave behind excess derivatization reagent. Then they need to change the solvent and run LC electrospray MSMS. So as I mentioned earlier, they do MRM, and you get a choice of two major fragments. It's either going to be the 146, which is the sodiated picolinic acid, or the M plus Na minus 123, which is the molecule which has lost picolinic acid. And they do get very nice data for in serum analysis. They see a very nice number of oxysterols, and the sensitivity is good. So again, if we can just look at the merits of this method. So it's based on MRMs. Sensitivity is good, really good actually, 2 to 10 femtograms. They can work with as little as 5 microliters of serum, and at these amounts, you've got limited detection of less than a nanogram per mil. Also, as I mentioned on the last slide, they're able to get rid of excess derivatization reagent via simple hexane extraction. This is good, and it stops you clogging your LC column. So the disadvantage of the of the method. So one of the advantages of the method was that you didn't get many fragment ions, so you could do you get MRMs, which gave a lot of ion current, but that's also a disadvantage in that the MSMS spectra are pretty uninformative. So IDs is going to rely on chromatographic separation. You're going to need to separate out all the different isomers, and you're also going to need to have authentic standards. I'm always a little bit concerned too about in the derivatization reaction, they heat the reagents to 80 degrees. So this is a little bit warm for my liking, and I personally would be a little bit worried about autooxidation. So maybe it's best to carry this out in an inert atmosphere. Okay, so that was picolinic acid. There's another method where instead of using picolinic acid, nicotinic acid is used. So nicotinic acid is an isomer of picolinic acid. It's again, we're going to do the derivatization, and we're going to make the oxysterol ester. These are slightly different derivatization catalytic cocktail. That doesn't really matter. The reaction still goes very nicely, and they get the double derivative of the nicotinic acid ester. In this case, it seems that protonation is more prevalent than sodiation. However, the fragmentation spectra show characteristics very similar to those of the picolinic acid, in that you get fragment ions which are essentially the nicotinic acid, protonated nicotinic acid, or the molecule which has lost the nicotinic acid. So again, you get rather little fragmentation, but this is good if you want to do MRMs. Okay, so that's picolinic and nicotinic acid ester derivatization. Let me now move on to perhaps the most popular method of oxysterol derivatization at the moment, and this is derivatization to make dimethylglycine esters. So this comes out from the work of Jiang and in Zilan Han's lab, and they were working with Daniel Ori. And they make a very nice use of this derivatization reaction in the study of Niemann-Pick disease, in the diagnosis of Niemann-Pick disease. So this is a method which is being quite well used now throughout the world. So let's look at the method. So again, we've got our oxysterol. In this case, we've taken 7-ketocholesterol, and we derivatize the 3-beta hydroxyl group, and this time we convert it to a dimethylglycine ester. So the nitrogen group of a dimethylglycine is a tertiary nitrogen. That means it's readily protonated. So this will be readily protonated in the electrospray ion source. So we'll get the protonated molecules, so we get a nice signal. When we do MSMS, we get fragmentation due to the loss of the dimethylglycine to give either the protonated dimethylglycine ion or the M plus H minus the dimethylglycine moiety. So again, this is very nice for MRMs. So actually, Daniel Ori has really used this method very impressively in studies looking at Niemann-Pick disease, and actually identifying patients with Niemann-Pick disease due to elevated levels of 7-ketocholesterol. So here's our Niemann-Pick patients, and here are controls. And in nearly all our Niemann-Pick patients, you can see we've got an elevated level of 7-ketocholesterol. And this is done by using the simple derivatization. Another molecule which is elevated in Niemann-Pick disease is this one, which is colestane 3-beta 5-alpha 6-beta trial, and that one's also elevated in Niemann-Pick. So in the one derivatization, they're able to derivatize both of the molecules, analyze them both in the same LCMS, and really get quite excellent identification of Niemann-Pick patients. Some figures of merit really for this method. The derivatization is one pot. So it's all done in one go. They use quite low levels of derivatization reagents, so this is good, so they don't have problems of clogging up their LC columns. Using MRM detections, lower limit of quantification, 2 nanograms per mil, so that's perfectly respectable. Disadvantages, we actually, like most of the other methods, the ID relies on chromatographic separation of all of those isomers. If the isomers are overlapping, you're in trouble. And you also need authentic standards to make sure that what you're looking at is what you think you're looking at it. I'm always concerned with autooxidation, so that's always a worry. Okay, in the final few minutes, I should just mention the methods that we like to use, and also some friends in Norway. So we use LC electrospray, MSNS and NSMS. And we like to do a double derivatization reaction, where in a first step we use an enzyme, and then the second step we do a derivatization. So most oxysterols have this 3-beta-hydroxy 5-ene function, and you can convert the 3-beta-hydroxy 5-ene to a 3-oxo-4-ene using cholesterol oxidase enzyme. So you just buy the cholesterol oxidase enzyme and you can convert the 3-beta-hydroxy to a 3-ketone. So this adds specificity to your method, because you made your method now specific for cholesterol and cholesterol-like molecules. It's specific for sterols and oxysterols. Once you've got the 3-ketone group, you can do a bit of chemistry. So we like to use the Girard P reagent. You can just buy this commercially. And this is a hydrazone. So this is a hydrazine, and a hydrazine will react with the ketone to give a hydrazone. And as the Girard reagent has got a quaternary nitrogen, which is charged, you effectively tag a charge onto the molecule. So we call this method enzyme-assisted derivatization for sterol analysis. So you see where the name comes from, the enzyme-assisted derivatization. So we get 2 advantages really with this. We get good signals because we're adding the quaternary nitrogen, and we also added specificity because we're using an enzyme. Oh, just a little cartoon to show you the method. So oxysterol, if you just analyze it on its own, get not a very big peak. So we first treat with cholesterol oxidase and introduce the ketone. Then we add the Girard reagent, and if you look, the peak goes up by a factor of 100 to 1,000, depending on your ion source. So we use this method almost exclusively. Another nice thing is when we add the Girard reagent, we tend to get useful fragmentation. So if you just do a simple MSNS, then the major fragment ion is due to the loss of the pyridine group. So you see M minus PY, and you see a little bit of ring fragment ions as well. So if we just simple MSNS, here's our parent ion, major fragment ion is due to the loss of the pyridine. So this can be useful if you want to do MRMs. But we like to do actually, we like to do MS to the 3. So we like ion traps. So when we do MS to the 3, in the first step, our MSMS step, we lose the pyridine to give us the M minus PY. And then once we've got this, we fragment it again in the MSMS step. And when we do that, we get fragmentation spectra, which are really rich in information. So we get fragment ions from the ring fragmentation, and we also get fragment ions in the side chain. So this is really useful because you can pinpoint the position of oxidation of any oxysterol. So this is really useful for the identification of unexpected oxysterols. So just to show you some MS to the 3 spectra, I'm running out of time now, but you can take my word for it, but the MS to the 3 spectra of different isomers, they're all different. Figures of merit, well, the most important really is that we can differentiate between isomers and we get good sensitivities. And the disadvantage is really, as with all derivatization reactions, you can get side products You also have problems with excess derivatization reagents. One final slide is we can also do on tissue derivatization, so we can then do moldy imaging. So this is a moldy image of cholesterol in a mouse brain. So I think I've almost gone over my time, so I'm going to finish there.